All right. In this video, I'm going to be talking about tangent planes and normal lines, and this is something we can, do with our partial derivatives. So, we've got a function z equals f of x and y, which is going to give you some sort of surface in space, and we might be interested in if it's differentiable, laying in a tangent plane to it. Okay, and then also we might be interested in a normal line for reasons that I feel like have to do with motion and stuff. We saw the relevance of a normal vector to the path of an object moving in space, and kind of similar situation there. So what I'm going to do is I'm going to, this is interesting. I had set out I'm actually going to define the gradient first. But I think before that, I am remembering that I recorded a video about equations of lines and planes in space, and then I didn't actually do that. I just did like dot product and cross product stuff. So I'm going to, just remind you that the equation of a plane in space is going to be, it's going to be linear in x, y, and z. Okay, you can solve that for z equals, linear in x and y. Okay, that will give you a plane. Okay, a line, notice if I do solve this for z, it's got two free variables. It's got x and y. Whereas a line only has one free variable. Is going to be, we're going to have to define it parametrically, okay, with some sort of parameter. Usually time, say L of t is, and we write it as a vector. Okay, so it's going to be, some where x, y, and z are all linear functions of t. So what we can do is we can write it as a point.
Wouldn't it not be a line if there's three? You could call it a line.
Yeah, it's a line. It's in 3 dimensions. The plane is where z is a function of both x and y, and all 3 of these depend on. Let me just, you know this. You just last time wrote me the equation of a line parametrically, and it was really nice. So I know you know how to do it. Okay, and then we can kind of do this. If we have a point in space, we call that ABC, and we have some trajectory, which I will draw in red, which we call the vector x, y, z. Then the line that, then this whole line here, this is, a plus xt, b plus yt, c plus zt. This is something that, that we did a lot in linear algebra. This is mainly for anybody that didn't take linear algebra, how to write the equation of a line, and just reminding you that, okay, it's going to have, the line is going to have time in it, and it's going to have like 3 separate equations, pretty much. Okay, now I'm going to tell you about the gradient. Okay, let f be a function that takes Rn into R. Then the gradient of f, which we use like an upside down triangle for, the gradient of f is the vector composed of all of the partial derivatives. Okay, so the partial of f, let's give that a capital, partial of f with respect to x1 all the way down to the partial of f with respect to xn. Okay, in the nice z equals f of x and y case, it's the partial of f with respect to x and the partial of f with respect to y. But I'm opening this up for maybe higher dimensions later. And the actual, what the gradient represents, what we're going to use it for, not part of this video, but I'm just telling you it's a nice way to package all of our partial derivatives, and we're going to need all of our partial derivatives to write down the equation of a tangent plane or a normal line. Okay, so I'm going to say, I think next we would talk about the actual tangent plane. The tangent plane to, z equals f of x and y at the point x0, y0, and z0 is, okay, hold on. It's exactly what you would expect, honestly. It's z minus z0 is equal to the partial of f with respect to x. Just for simplicity, I'm going to call that fx times x minus x naught plus fy times y minus y naught. You will see other more complicated formulas for this out there. This is the way to go, though. It's like point slope, right? Point slopes. Something like that. All right. And one thing that I told you in linear algebra was that if you have a plane, suppose I'm just going to draw you a hypothetical plane here. I've got this plane P, and P has the equation, 2x plus 5y minus 10z equals 1, then the vector 2, 5, negative 10 will sit normal to the plane. That's the normal vector n. Normal vector is equal to 2, 5, negative 10. That's a fact. This seems kind of like, it shouldn't be the case, but if you actually look at, y equals 2x or something, in the plain, old-fashioned y equals mx from Algebra 1, and you think about the vectors, it actually works there too. It's just we've never thought about it like that. Okay, so if I'm interested in taking the tangent plane and normal line to a function, I know just the function, g of x equals 5 plus x squared plus y squared. We've been working with this one today. So for example, z equals 5 plus x squared plus y squared, and we want the tangent plane to the function, or to the surface, at the point where x is 1 and y is 2. Okay, so the instructions are like find tangent plane above 1, 2. Okay. So first we're going to need a point. We're going to need our x naught, y naught, z naught. We have x naught, y naught. Okay, so it's 1 and 2, so it's 5, 6, and 4 is 10. So my point is 1, 2, 10. Okay, I'm going to need my partials. Okay, so the gradient of z is equal to, well, the partial of z with respect to x is 2x, and the partial with respect to y is 2y. Right? Because 5, I take with respect to x, say 5 is a constant, and y squared is also a constant. You think about it, it's 10. Derivative of 10 is 0. Okay? And so that's, the partial of z is 2x, 2y, so that's 2, 4. And now what I'm going to do is I'm going to, what was I saying? Oh yeah, I've got the point, I've got the trajectory, I'm ready to write the equation. The equation is going to be z minus 10 is equal to 2 times x minus 1 plus 4 times x minus 2. And I'll get out of the way in a second.
Wait, what? Oh, never mind.
Okay. That is the equation of the tangent plane. All right. It was pointed out that I'd written an x where I meant a y over there. Okay, and so that's how we write the equation of a tangent plane. Okay. The normal line is going to be just, the line that goes through the point of tangency and is normal to the tangent plane. Okay, so we're pretty much all the way there. We just need to do a little bit more work to get this going. I probably should not have erased that, but you know, this is big. So what I'm going to need to do is I'm going to need to get the normal vector to that plane, which maybe after you do this a couple times, you'll be able to extract it mentally, but I'm going to just, you know, kind of carry it all the way through. So if I'm, you know, trying to find the normal line, I have the point, and the point is 1, 2, 10. And then the trajectory is going to be, well, I need to kind of, in order to get the normal vector, it's best for me to write it ax plus by plus cz, you know, and a number equals 0. Or ax plus by plus cz equals a number. We don't really care about that. What I'm going to do is I'm going to do a little bit of working around on this. And so I'm going to have a z minus 10 minus 2x plus 2 minus 4y plus 8 equals 0. I don't really care about the numbers because that's just kind of saying where the plane is. I'm concerned more with the trajectory. I've got negative 2x, negative 4y, and positive 1z. So my normal vector is negative 2, negative 4, 1. Now, you may have solved this a different way. You may have pushed the z over to the other side, and you may have had 2, 4, negative 1, and that's fine. The orientation of your normal line will be the opposite of mine, but it's the same line. It traces out the same line in space. So I've got a point, I've got a vector. I'm going to write the equations for the line, or the vector equation. Normal line is 1 minus 2t, 2 minus 4t, and 10 plus t. And that's all I've got for you for today.